Hi, my name is John Kingham, and I am the host for today's webinar. John Frederick will be presenting. John has been with Bently Nevada for 19 years, working in the field services group as a site lead. He has a mechanical degree or engineering degree from the University at Buffalo, and in his tenure at Bently Nevada, he has designed and installed transducers on a variety of machines, including wind turbines, large steam turbines, gas turbines, hydro turbines, reciprocating compressors, feed pumps, and motor-driven fans. We are recording today's session, and in order to make these videos worthwhile to you and your colleagues, we ask that you make sure that you are on mute and refrain from broadcasting your video. We are also using the Slido app for questions. I always recommend voting for your own question. It gives it extra priority. And as we are recording, we will wait until the end after we stop the recording to pose and answer the questions in the queue. With that, thank you for attending, and I'd like to turn this over to John.
Hello and welcome. Thanks for joining. I'm going to apologize right now. There is a thunderstorm in my area, so hopefully I don't lose power from that, but you might hear some rumbles in the background. I'll try to talk over them and push on through. But today I work for the Design and Installation Services Group. I've been with them for quite a while, and so we want to talk about some installation considerations around proximity probes on rotating and reciprocating machinery. Little plug for my group that I work in, the Design and Installation Services. We have field engineers, and we can execute projects from start to finish, all the way from conceptualization through startup services. We offer electrical design services, mechanical designs, and we actually come out to site and do the mechanical designs, measure the machine, make sure everything's going to fit. We offer project management services. We also manage subcontractors if you want us to manage the electrical implementation, mechanical implementation. We get the brackets made and install everything, and then also documentation's included. So we offer electronic or paper copies of all the drawings, do a write-up report, include pictures and whatnot. So we do this all day, every day. Bently's been doing it for quite a while, a couple of decades. So we have quite a bit of expertise in it. So we can help you to avoid some common pitfalls, and might actually save you some money by using our services, since we have the experience. So with that, one of the things we have to consider anytime we're working on these machines is the shaft material. It's important to know shaft material because our proximity probes are calibrated to read AISI 4140 steel, and using any other material to view the shaft, to use our probe to view a different material, it can cause a erroneous reading. So your scale factor might not be accurate, and it can give errors. So it's important to have the proper instrument for the material. We have a huge database where we've taken our standard prox probes and run them on various materials and recorded how they vary from standard AISI 4140. So if you know what your material is and you give that to us, we can tell you how close or how far away it is. If you're 1 or 2% away, typically we just stick with the standard that is just a minor error, and then you can get parts quicker and not have to do custom parts every time you need a new proximeter. If it's further off, we may need to evaluate what the best path is, and hopefully we have a material for you. So if you're not sure what your material is, how do I determine that? There's a couple of ways to go about doing this. Typically the easiest way is to ask the equipment manufacturer, contact your turbine OEM, your pump OEM, and ask them what material is in your shaft. Quite often they use some sort of proprietary material that they might not be able to tell you the exact composition, but Usually they can tell you it's very similar to a common alloy, and that's usually close enough for us to get within that 1 or 2% range and figure it out. If not, there are devices that can analyze the shaft by checking a whole bunch of sciencey stuff. I'm not sure exactly how they work, but I have had customers that have checked their shaft with these gizmos to come back with a rough composition of metal to get an idea of what type it is. So those are a couple different methods for doing it. We also can just take a standard prox probe and run a curve on the shaft and verify how close or how far away it is from a good reading on AISI 4140. And you might say, well, what's the worst that could happen? It's like it's a metal shaft. It should be close enough. And the problem is some metals react differently to our sensors. So you could end up with an incorrect view of what your reality is inside your machine. And you might think that you look like this guy on the right when you actually look like an average human being. So it's best to make sure you have the right material and the right prox probe so that they line up so that you are getting good readings and you can trust your data. So once you know your shaft material, surface finish is important. So it's, do I need to, or can I just put my probes anywhere? And as you can see in this picture, this shaft has had some damage done to it by something. I'm guessing somebody was rotating it with a large pipe wrench or something right there. I'm not 100% sure if the how mucked up the thrust surface is there that collar that probe is looking at, but you definitely would not want to look at this for radio vibration right there, because that's you're definitely going to see that on the prox probes. And what those marks, what we like to refer to those are glitch or runout. And that's where there's an imperfection in the shaft and the prox probes are going to view it, and it can cause errors in the readings from the prox probes. This does not include field wiring interference. If you ran your field wiring incorrectly, used unshielded, ran it in a cable tray with power wiring, that type of stuff, improper mounting, loose brackets, that kind of stuff, that's not considered runout. Or other mounting issues, if you mounted it too close to another transducer, whether it be a magnetic speed probe or another eddy current or proximity sensor, those are different considerations altogether. So we're just focusing on issues with the shaft surface that the prox probe will see that can give us erroneous readings and bad vibration readings. So on the previous slide, that was what we would refer to as mechanical induced runout, and that's when the surface has been improperly machined or damaged, and it will yield some sort of sinusoidal displacement signal with a frequency coincident with a rotation speed. Basically, just your slow roll vector when the machine's going slow and there's no vibration, and you actually see what looks like vibration. Sometimes this is caused by non-concentric rotors. If your surface where you're looking at where the probe is looking is not perfectly aligned with the rest of the rotor, having a bowed rotor can cause mechanical runout. That would be eccentricity typically. Surface irregularities, like we saw, scratches, dents, burrs, and then uneven plating is another big one. We run into plated shafts a lot on feed pumps, where there will be some chrome plating around the bearing area, and depending on how thick that plating is, if it's not an even thickness all the way around, our prox probes can sometimes read through that. So it's best to verify how thick the plating was. If it was only like 5 or 10 thousandths, we would recommend you have that rotor turned down and plated thicker, so we can just use a chrome proximeter for that alloy of chrome to view solid chrome. So basically what can happen is the surface physically, like with a dial indicator, can look like it's a perfect circle, like the yellow line, but your prox probe will see the red line because of the plating issue. or if there's scratches or dents or something like that, those are typically more visible. So in addition to the mechanical runout, we also have electrical induced runout. And our proximity probes are an eddy current style probe, and so they are very susceptible to electrical interference. And the electrical runout that we run into most often are caused by these. We have residual shaft magnetism, precipitation hardening, metallurgical segregation, surface microcracks, and stress concentrations in the rotor. So depending on where those issues might lie, if our probes come across them, they will definitely see them, since the eddy currents penetrate into the shaft a little ways, and that can cause some readings that might look like there's vibration there that is not actually there. So some consequences of having glitch or runout, it can make the curve on the left look like the curve on the right because of some scratches in the shaft. And in this example, it looks like the scratches are probably about an additional 50% to the total vibration that you would see if those scratches weren't there. So it can be fairly significant. So scratches, electrical runout, magnetism, that type of stuff, it can make the apparent vibration levels higher than what are actually present. Could cause you to trip off when you didn't actually need to trip a unit, or decide to shut down and inspect it. And looking at some of the vibration plots, it can add wings, as we call them, to our orbit plots. So if you look at this plot on the right, most of the vibration is at top of the center portion of this plot, but it's got a scratch or something that's causing the probes to have a blip both on the X and the Y side of the orbit. That gives it these wings, and in this case, the direct reading is probably going to be about 4 times higher than what you would actually what the actual levels are, because of these scratches being so large in comparison to the total amount of vibration that is present. So identifying glitch and runout, there's quite a few ways. For mechanical runout, visual inspection and touch are some of the most common ways, just to verify whether or not you have some erroneous issues. If you can see it by shining a light on there, and you can pick it up with your eyes, and the transducer system is probably going to see it. If you see something, it's best to touch it, and if you can feel it with your fingernail, our prox probes are going to see it. Our prox probes are very sensitive. They can easily sense down below a ½ mil of vibration. So that's a very minuscule crack. So it's best to check your surface areas where you're going to be putting the probes to make sure that they are free of glitches as much as possible by feeling them or touching them. If possible, roll the rotor around to check all sides of it. You'd hate to pick a spot and then bottom dead center where the rotor was sitting, there's a giant scratch or a screw in your way or something that's going to cause issues. And then for the electrical runout, that's not something that we can visibly see, so we have to rely on some sort of electrical instrumentation, such as we have a Scout portable walk-around system that can be used to collect data, samples on the shaft. And then electrical instrumentation for glitch detection can also be used beyond that. Gauss meter is one of the more common ones to check for magnetism. And it's best to measure your glitch outside the machine. And this applies to both mechanical and the electrical. Taking it outside of the bearing journals, it eliminates any issues. Trying to keep that rotor bottom dead center and around bearing journal is not the easiest thing. Rollers can be used, but it's better to use a V-block with a piece of Teflon in it to make sure you don't have any issues with run out of the rollers or debris on the roller surfaces. So identifying glitch or run out is actually not too hard of a task. If you have an Adre or a System 1 hooked up to it to take vibration readings, turbo balance, something like that. On slow roll, it's usually pretty easy to identify. In this instance, we have about 20 mils peak to peak for our slow roll, and looks like it's up and down, but there's also a spike in the middle of it as well. So definitely got some run out of some sort going on here, whether it's electrical or mechanical. So it's easy to identify that it's there, but trying to measure it exactly can be a bit more difficult to take care of. So API 687 has some recommendations on measuring glitch, and API, for anybody who doesn't know, is the American Petroleum Institute. They put these lists together, and we reference them quite often. There's quite a few API documents that I've run across in my tenure with Bentley and working in vibration monitoring systems. But these are some of their recommendations. As I was talking earlier, using V-blocks to support the rotor, so you're not relying on the bearings or using rollers. Best to use an eddy current probe system, such as a Bently Nevada 3300 prox probe. Ideally, you want to use the same probe that you're going to use to monitor this rotor with in the final setup, so that you can make sure that it actually functions as expected. You want to try to get a mechanical readout, such as a dial indicator, and you want that to be in line with eddy current probe, but you need to make sure it's far enough away from your eddy current probe that it doesn't cause interference. And then you should have a phase reference mark, such as a key phaser, or you could use optical tape with a laser or something like that. So when you're recording your readings, you can see how much one revolution is rather than trying to guess at it. So you know where your rotation starts and stops. And then magnetism detection Gauss meter would be highly recommended as well. And then measuring your runout, you want to be perpendicular to the V-block support surfaces. So if you have your rotor supported in V-blocks like this, that would be a correct location to measure your runout, because you're measuring the diameter of the shaft, and it's always going to have a constant reference point from that V-block. Measuring top dead center in this instance is technically incorrect, because there could be some variance based on exactly how that rotor is sitting in the V-block, and if there's a flat spot on one side of the rotor, it could cause the numbers to be harder to tell where the runout is. So it's best to keep it in line with one of your V-block support surfaces. So I've got some examples of runout testing that I got from one of my colleagues, and this is the key phaser probe mounted up here, and you can see that one of the rotor supported on the left-hand side in a V-block with a piece of Teflon underneath it to allow it to spin freely. And then on the other end, they had the other end supported in a V-block as well, and had the probe looking at the surface. And I can tell by looking at this that this surface has been turned down slightly. Probably some grinding was done to clean up that area. And as we were just talking about the proper location to measure this, according to API, this is not the proper angle to measure this. They should be at either 45 left or 45 right to eliminate any reading errors. Also, I don't notice a mechanic dial indicator on this, so I would have added one of those as well, just to correlate the prox probe readings to the readings from the prox probe to make sure that they're in line with the mechanical readouts. So we've talked about measuring glitch, but how much is too much? The ISO, which is International Standards Organization, I believe is what it stands for. They've got a document 7919-1 talking about mechanical vibration of non-reciprocating machines and some guidelines. And they recommend that the total combined electrical and mechanical runout, as measured by the transducer, should not exceed 25% of allowable vibration displacement, or 6 micrometers, whichever is greater. And when I read that, I'm a little confused because I'm not sure exactly what that term allowable vibration is. So digging a little deeper into this to figure out what allowable vibration is considered, they talk about these zones. They have zone A, which is the vibration of newly commissioned machines, would typically be in that zone. Zone B is where you're is the a long-term operation within that zone is perfectly acceptable. And they recommend using the zone AB or the AB zone barrier for new machines or the BC limit for older machines. And this is a chart that I pulled out of the ISO 7919 to kind of give it a more graphical sense. I like learning by pictures. But the x-axis here is the shaft rotation speed. The y-axis is the peak-to-peak shaft vibration displacement. It's measured in micrometers. So this is a general guideline. You can figure out what the machine speed is and then figure out what the vibration limits are. So the A zone here is typically what a new machine you would expect to see it in. The B zone is an older machine, should always be in that zone. C is what you would consider the alert or the high zone. And then D would be your danger, your trip, your high. So typically you're going to be at this BC barrier for what your alert limit would be, and then you would want to go down to 25% of that for your allowable. But keep in mind that chart and these ISO 7919 are statistical values only, and they can differ from the alarm and danger values you use for your machine. Some turbine OEMs have really good data on where they want to see their alert levels at, and they might differ from the 7919. So if you can talk to your turbine OEM, pump OEM, find out what their recommendations are, or if you have some operating experience with that machine and know what it can do, that's always a possibility. So it's recommended, as I was saying, that the total combined electrical and mechanical runout, as measured by the transducer, doesn't exceed 25% of the alert limit. That's a general rule of thumb. So if you had a machine that has 6 mils of vibration, the total runout, mechanical and electrical, as seen by the transducer, should be below 1.5 mils. So we've identified the glitch. We know how much is too much. Well, if we have too much, how do we get rid of it? So mechanical runout can be removed by putting the rotor in a lathe. Once again, we want to use V-blocks to support the free end of the rotor. Don't use tailstock. From the lathe, it's best not to use rollers. So this way we can ensure the runout will be removed and everything's going to be perfectly circular with the bearing. Use an expert lathe operator if you have to do this. If you can find a shop that has lathe operators that have removed runout before, that would be advantageous to work with them. And I think the other big thing to be sure to do is that you do a new runout test at completion of doing the runout or of doing the reduction of the runout. And then for electrical runout, burnishing of the shaft is one option. Usually it's diamond burnishing, degaussing the shaft if necessary. There's a couple methods to try to do that. And then once again to try to perform a new runout test at completion to ensure that you have gotten rid of or minimized your runout as much as possible. And here on the right is a picture of a shaft that has been ground down a little bit in this area for the probes to view so that they get a better reading. So when you're finishing these Surface finish, our recommendation after grinding or burnishing is that the surface finish should be 16 to 32 microns. Grinding often produces magnetism, so check for magnetism after grinding and degauss if necessary. Once again, that's why we recommend doing runout checks after you've done any runout reduction, just to verify that there is not something else going on there. This is a picture of a shaft that has been diamond burnished in the radial probe viewing area, as indicated by the arrow. So you can see it's a slightly different color than the area next to it. So we've done all this work to try to make our areas nice and shiny. We definitely want to protect your viewing areas on the shaft. So to keeping them protected, we want to educate any craft that's going to be working on these about these areas to make sure that they're careful around them. Covering them with something such as some 1/8 inch or 1/4 inch rubber to try to protect those areas in particular, especially if the rotor's coming out and going to be shipped somewhere, to make sure that stuff doesn't get dropped on it, and in general, prevent dropping objects and tools on the rotor to try to eliminate any issues of any runout being induced while this machine is being worked on. So some people might have a question about, well, what happens if I can't get rid of my runout? It's just going to be too expensive to try to remove the rotor. It's not going to be coming out for another 2 years or 3 years or whatever. So what options do I have? And we do have some options. They're called circular acceptance regions, or CAR. And I want to stress these are just a temporary solution. They should only be used when the glitch or runout cannot be removed or corrected. We can compensate the 1x, which is the component of the vibration at running speed, and then the 2x signals, which is the component at 2x running speed. And essentially, we're putting a vector of displacement at a specific angle to try to filter out the runout that we can't eliminate. And we have a couple options. We can implement this using our System 1 software, and we also can implement it using our 3500 hardware if you don't have System 1 and you're interested in doing this. Now, one thing to mention about doing it in the 3500 is that this is only going to pass through anything that's at machine running speed or 2x running speed. And there are many machine fault issues that are relevant in the direct signals that are not at machine running speed or 2x. So if you're going to do this in the hardware, we recommend using a second card for the circular acceptance region. So for instance, if you had a feed pump that had a chrome shaft on, say, bearings 3 and 4, you'd run bearing 3X and Y into channels 1 and 2 on slot 5. You'd run 3 and 4 into, or run bearing 4 into channels 3 and 4 on that same card, and then install a new card adjacent to that, parallel your signals over, and then configure your circular acceptance regions into that new card, so you have your direct readings as well as having the 1x and 2x in the adjacent card. In Bently, Nevada, we do not recommend using electronic runout compensation if vibration monitoring system is wired for automatic machine shutdown. Doing the software version is fine, but doing it in the 3500 we don't recommend. So it's best to try to eliminate the runout, the glitch, ahead of time. So with that being said, kind of to wrap this up, know your shaft material, try to avoid your glitch and runout, surface preparation, and then make sure you protect your probe viewing areas.